Alright, so this particular video will contain the second part of applications as far as solving quadratic equations. And so these applications in particular deal with how we solve quadratic equations that may not necessarily look like quadratic equations, and in particular whenever we're wanting to use a strategy of substitution. Okay, so the first example here is a pretty straightforward one where we see that we do have a quadratic equation, but for whatever reason here we see that we have x plus 7 written here in parentheses. So this would be a situation like if we had a composition function where our inside function was x plus 7 and then our outside function was 3x squared minus x minus 4. And so we were trying to solve an equation like that involving composition function. But anyway, we see here that x plus 7 is in the parentheses here. And if we just looked at this as something like u, then we would see that this would be a traditional quadratic equation that we're used to. So what we want to do here is we want to let x plus 7 represent some other variable. I'm just going to call it u. And then from that, we rewrite our function here and thus our equation. And so the reason I'm saying that is this is our function, and if we're trying to find the zeros of it, then our equation is going to be this function equals 0. So we're going to say 3u squared minus u minus 4 is equal to 0. Okay? And so in doing this, we're making this problem easier by substituting for u, but we're going to have to pay for it at the end by substituting back in what u is. And the reason for that is, remember, we're trying to solve for x, not u. So anyway, we keep going here. We can go ahead and factor this out. And so this would be 3u here, u there. And one of these would have to be a plus, one of these would have to be a minus. So I'm going to go with minus here and plus there. And of course, the factor of 4, I could use either 1 times 4 or 2 times 2. And so I'm going to elect to use 1 and 4 only because I see that the difference in between the factors here needs to be a negative 1. And whenever I multiply that times with 3u, it turns out that with the 4 being there and the 1 being there, if I multiply this, I get a minus 4u. And if I multiply that together, I get a plus 3u, which gives me a negative u, and that's what I need. Okay? So from that, I go ahead and I say now 3u minus 4 is equal to 0, or u plus 1 is equal to 0. And so I'll go ahead and solve for u now. So I add 4 to both sides, and then divide by 3. My u is 4/3. Or if I subtract 1 from both sides, my u ends up being negative 1. So I have the answers of u being 4/3 or u being negative 1. But you have to remember here that we're not solving for u, we're solving for what? That's right, we're solving for x. So here at this point, I have to go ahead and substitute back in what u was, which was x plus 7. Okay? And I'll do the same thing here. So x plus 7. So now what we have to do is solve this equation, and we have to solve this equation here for x. And so we'll go ahead and make some room so that we can finish doing it. All right, so now that we have our two equations together here, we can go ahead and solve both of them for x. So we could start off here by subtracting x from both sides and then changing it into a fraction. But I know a lot of people do not like fractions, so what we're going to do here instead is just get rid of the fraction by multiplying both sides by the LCD, which in this case is 3, since that is the only fraction that we have. So if we do that, that's the same as 3 over 1. That reduces to just 4 on the right, and we distribute. That'll be 3x plus 21. Subtract 21 from both sides. And so 21 minus 4 should give us a negative 17. And then we divide that by 3, and then we get negative 17 over 3. That's our first answer. Okay. Our second answer, of course, we come here, subtract 7 from both sides. Pretty simple, and we get x equals negative 8. So from there we see that the two values of x that solve this particular equation would be x equals negative 17 over 3 and x equals negative 8. And so where the x-intercepts, so of course we know that the x-intercepts are the same thing as the zeros. And again, this is not asking us to put it in ordered pair form, so we'll just type the same thing that we had before. Right, so now we'll go ahead and move on to the next application problem. All right, so for our next problem, we see here that we're wanting to find the zeros of, or the real zeros rather, of the function g of x here, and we can clearly see that g of x is not a quadratic function. However, we're going to use substitution to turn it into one that looks like a quadratic function. And so how we're going to do that is, if we notice that if we let u equal square root of x, which is the particular term here, or part of the term that's causing the problem, if we were to square both sides, then this would mean that u squared would be equal to x. Actually, it would be absolute value of x, but we're assuming that x is going to be all non-negative numbers here, so hence why we'll just say it will be just x. So in doing that, and I guess to clarify why we're saying that, is if we look at our function here, if you notice, the only thing that causes a restriction is the term here, negative 4 square root of x. And if we find the domain of this function, we know that square root of x must be restricted to being values that are greater than or equal to 0. So hence, what this tells us is that we can't have, we have to have non-negative values for x. So that when we come here and say u squared is going to be the same as, and I'll just go ahead and write it all out, this squared, which is absolute value of x. If x is greater than or equal to 0, then we can just assume that it's going to be x. So that is why I'm saying that. All right, so we'll go ahead and continue on now. So now that we know that we're going to replace square root of x with u and u squared with x, if we rewrite this problem now, we know that g of x is going to equal 0. Now that's going to be, instead of x, is going to be u squared, and instead of minus 4 times square root of x, it'll be minus 4u, and then we'll have minus 12 there. Okay. And so if we factor that, if we do this by trial and error again, we'll see that we'll have u here, u there. Since we have minus minus, one has to be a plus, one has to be a minus, and then from there we'll see that the factors of 12 that have a difference of 4 would be 6 and 2. And so since we need this number here to be negative, we put the large number 6 by subtraction sign and 2 by the positive one. And if we go check, we see that we end up getting a negative 6u plus a 2u, which gives us a negative 4u. So that's what we need. Okay. So now what this means is that u plus 2 is equal to 0, or u minus 6 is equal to 0. And of course, if we subtract 2 from both sides, that means that u is minus 2, or now that u is equal to 6. Okay. But now again, we are not solving for u, we are solving for what? That's right, solving for x. So here we have to substitute what u ends up being, or what u was rather. And u in this case was square root of x. So we're going to say square root of x is equal to minus 2, or square root of x is equal to 6. And so now what we need to do is solve these two equations. And when we solve them, we're going to take into account of what the graph of the function square root of x looks like in order to properly solve for these. So I'll clear some space for us to go ahead and continue on with this problem here. And one of the things that you'll see is that below I have the graph of square root of x drawn. And so if you notice, square root of x is a one-sided function here, where its domain is from x equals 0 to infinity. And of course, its range is from 0 to positive infinity. And so that's important for us, because whenever we look at this equation here, this first one, we're saying, all right, give me the value or values of x here on this particular graph that has a y coordinate of -2. And if you notice, all the graph is above the x-axis. None of it is below. So it's impossible for this particular graph to have a y coordinate of -2. Okay? So the answer for this particular equation would be no solution. Okay? Now, I know some of you are tempted to say, well, why can't I just square both sides? And if I do that, you would get x is equal to 4. Okay? If you actually went back in and plugged in that into this particular function here to see if you got 0, you would find out that you wouldn't get it. Okay? And the reason for that is here, if we take account into what the graph looks like, remember when we solve equations, we're only using, this graph here is only talking about the principal roots of x here, okay? So this graph sort of explains what we mean by the principal root. We mean the root that only responds to the graph. If we could do a point here on this side that was negative, then what we would have is a graph that looks something like this as well. The issue with that is that this particular graph here, if you notice, I could draw a vertical line through it. And if I was to draw a vertical line through it like that, then this would not pass the vertical line test, which means that this wouldn't be a function. And so this would violate everything that we're saying in this particular equation. So again, this is why at the end of the day, the actual answer to this portion of our problem here is no solution. So I'm going to go ahead and get rid of that. And so you could either write no solution in words, or you can just do this symbol here. Okay, saying the null set with no answers. Now for here, this would make sense, because now, let me go ahead and clean back up this graph some, make it look the way it's supposed to. Let's get rid of some of that. So if we come back here, we see that here when x is 36, this should map up to a y value of 6 here. Okay, so we know that, so if we come and square both sides here, this actually makes sense for us to go ahead and do that. And of course, this actually is absolute value of x, but when we know that x has to be greater than or equal to 0, that limits us to just being able to just, well, it allows us to be able to just say x. So the only real solution to this particular problem here would be x equals 36.